Welcome back to Physics 3740 at the University of Utah. Today we're going to be talking about the Schrodinger equation, which is maybe the most famous equation in all of, one of the most famous equations in all of physics, and certainly the most famous in quantum mechanics. So let's first motivate our discussion of the Schrodinger equation and our sort of heuristic derivation of the Schrodinger equation by thinking about other sorts of waves which we have encountered before. And one of the things, so we're going to be talking about primarily matter waves today. We've talked about matter waves before. We talked about de Broglie's hypotheses and so forth, that particles have wave-like nature and vice versa. And in some sense, all waves have some things in common. So, for example, very importantly, all waves have an underlying wave equation, and the wave equation contains all the physics. This is where the physics, the force laws, and conservation of energy and momentum and everything goes into the wave equation, and from that wave equation, you can solve for a wave function. Okay, wave function, and so we have a wave equation and a wave function, and the wave function conveys all the behavior. So this tells you how the wave evolves in time. Okay, and the wave function obviously must be a solution of the wave equation. And generally speaking, wave equations are differential equations, and usually second-order partial differential equations. Okay, and so it turns out the Schrodinger equation is just the wave equation for matter waves, or that's one way of thinking of it anyway. So we should think about wave equations. So all wave equations arise from fundamental laws. As I said, the physics is what goes into the wave equation contains all the physics. This is where we put in force laws and whatnot. Okay, and so just let's consider a couple examples before we get to matter waves. So we can think about mechanical waves. For example, if you have a string that has some tension, and you jiggle the string, you can get a transverse wave which propagates along the string. And in this case, the underlying physics, the underlying laws that govern the transverse waves that go into the wave equation basically come from Newton's law, Newton's second law, F equals ma, famous Newton's second law. So if we, again, were to have a transverse wave on a string, for example, the wave equation would look like this. It's v squared, where v is the velocity of the wave, is equal to the second partial derivative of the transverse displacement y, as it's the second derivative with respect to the direction x, which is the direction that the wave is traveling along. So it's the direction of the string. Okay, and that's equal to the second derivative of the transverse displacement y with respect to time. Okay, now here all the physics comes in basically determining v squared. So F equals ma tells you how the tension and the if you think about the tension in the string and the mass density of the string and so on, then that's basically how you solve that. Those give you a relationship for v, the velocity, and then this is the equation. And if you solve that equation, you get a wave function, which is simply just a sinusoidal varying function, a harmonic function, some amplitude a times sine of kx minus omega t, where again k is the wave number and omega is the angular frequency, and the velocity of the wave is, just as we said before, the phase velocity. And this is a plane wave solution, so this is not a wave packet. Okay, so the velocity of the wave is the phase velocity is equal to omega over k. Okay, and this is what such a wave would look like at a particular time here, and this would propagate with velocity v. So again, y gives the string's transverse amplitude as a function of the distance along the string and time.